Yeah, Anu and I will monitor that, Prabha. You just take those questions. There are some 4 or 5 questions that are generally asked, so we'll cover
Sir,
that
we have
first.
started the live.
Then
We can start, sir. We are live now in YouTube. Please start.
I think you can close this. The journal open.
And can we unmute ourselves then? Is it okay? Is it echoing?
Share okay. Thank you. So Anu, I think we are live. Do you want to start the proceedings?
Okay. Hello, everyone. Thank you for joining us on the live session of week 1 of Introduction to Quantum Computing, Quantum Algorithms, and Qiskit. So we had a couple of questions around course logistics, and maybe I'll go ahead and answer them. We have created a separate server, a Discord server, wherein we are a channel called FAQ. So I request you all who are on the other portal, which is on Google Groups, the discussion forum. We are also monitoring questions on discussion forum, but it would be great if you could all come to this platform called Discord. There's a particular course server. If you go to the announcement, I have put that announcement there, and the link to joining the Discord server is also there. Once you join Discord server, there are multiple advantages. There are several channels in here, respective to the each week's course, the assignments, and in general, if there are questions around IBM Quantum or Qiskit or programming, we have separate channels where people can help you. And not just the instructors, we have a group of mentors who are extremely qualified to answer most of the questions, and they are very active. They have been actively responding to all of these questions, and 24/7 you can get that support. So all your other peers can also answer some of the questions that you might end up with in some time. So I would strongly urge you all to join Discord server and make best use of Discord server. Now, coming to the FAQ channel, I have bundled a couple of questions that are there. You can just expand and view the entire file here. I'll go briefly over a couple of them, which I think have been pertinent questions, and several times the mentors or the instructors have answered these questions. If you there are certain questions about prerequisite. If you go down to the course portal, prerequisites are clearly defined. Questions around if you are in 11th or 12th standard and whether you should take it or not, you're most welcome to take the course and earn the certificate. This certificate will be useful for you in future, and you can put it in your CV and amplify in your social medias as well. And students who are enrolled in an AICTE approved engineering curriculum can also use the 1 credit for their credit completion in BTech, MTech, or PhD program, wherever you're enrolled in. There will be no live lectures. All the lectures have been pre-recorded and are available on the course portal. Once you go to the dashboard, on the left side of your screen, you can see each week, and under each week you can see all the weekly content, the assignments, and the feedback form. We request you to submit your feedback so that we know what better we can do. Also, please feel free to use the feedback channel in the Discord server to let us know of any other things that you would be needing during the course. There are the PDF and the notes for the lectures and the PPTs, and all of that would be posted soon from the NEPTEL organization, and they will all be there on your under each week content. Once they are available on the course portal page, I will also make an announcement on Discord server. Regarding background, so we have a lot of people asking if they're coming from physics background or they are coming from maths background, but do not have a lot of coding experience. Will it be very difficult to grasp Qiskit? We would say that if you are coming from maths background or physics background, it's going to be helpful. It's going to be very helpful to learn quantum concepts, so it's a huge plus. And if you have any prior knowledge on any high-level, programming language, C, C++, then Qiskit should be very easy to pick up. Also, in IBM Quantum experience, you have a graphical user interface-based circuit composer where you can drag and drop and create circuits. So stay tuned for the next week. So week 2 will cover a lot of the programming exercises. We'll show you how you can code up in using the graphical user interface as well as Qiskit. Regarding programming assignments, week 2 and week 3 are going to have some programming assignments, but the programming assignments are intended to enable learning so that you understand how to run a code on Jupyter Notebook, or where are the places where you can go and run. What are the different resources that can help you learn Qiskit programming, and Qiskit textbook is one such fantastic resources. All of that would be there. So that's the kind of assignments. And in the assignments also, we'll be sharing some Jupyter Notebooks which would have clear instructions on what to code. And there are parts of the code which are already written, and you'll have to just run and learn for yourself how are the different visualizations and how to run on an actual quantum computer versus a simulator and so on. There were questions regarding internship opportunities. So NPTEL has a portal, and I've put that portal link also on the FAQ document. So go out and reach out to NPTEL if you have further questions on that. And for general internship opportunities, so if you have these kind of certifications or these kind of courses, you're definitely better placed to get internships or internship opportunities in research or industry. And there are a lot of registrations that we see are outside of India, and there are some students who are currently in India but will not be there till October. And there have been a lot of questions around final examination. Since final examination is a proctored examination in India, and also in UAE, they do have a proctored examination where you go to the center and do it. But there is a provision of having an online examination. So please go to the FAQ document, and you have to email to this particular email ID, and NEPTEL folks are going to help you with that as well. So those are a couple of important answers or important questions that have been coming up multiple times in both Discord server as well as on Google Groups, and I hope I've answered most of them around the course logistics. So without further ado, I wanted to spend this 1 hour onto the actual technical questions. I know the mentors have been doing a fantastic job in answering several of them. But since Prabha, you are here, I wanted to ask you a couple of questions. And one such category of questions, and there have been a lot of questions, some of them have been answered. But maybe since you are here, could you please clarify the concept of state space size that was explained in the lecture of quantum computing basics?
Yeah, hi Anu, hi everybody, good evening, and good evening to all our participants. It's great to see the response that the course has been having, and great to see all the questions. We've been trying to answer as many as we can, as Anu said, on the Google forum as well as on Discord. Let me share screen. So, do you see the notebook here? Yeah, okay. So the question was regarding the quantum state space, right? And this is something that gets covered in the second lecture of the module, which is the first lecture on postulates of quantum mechanics. Right? So let me just number this so that we just keep track of what we discussed today. Yeah, so the idea is, so the question I think was, what is the difference between the classical state space and the quantum state space, and how do we understand this difference? So the way that we can think about this is, of course, just to briefly recap what I say in the lecture as well. So the classical bit, right, is just an object that takes one of these two values, 0 or 1, whereas the quantum bit is something that can exist in a linear vector space, that is spanned by the ket 0 and the ket 1. So what do we mean by this? And this indeed is the quantum state space, what I also call the quantum state space in my lectures, right? So to be precise, the quantum state space technically is what is called a Hilbert space, right? But as I mentioned in my lecture, we don't really need to understand Hilbert space at this point for the purposes of our course. It will suffice to say that this is nothing but a complex linear vector space that is equipped with an inner product. Now, the key aspect of a vector space that becomes important to us is the fact that, so let me just go over maybe briefly the properties of a vector space, and maybe that will help us understand what is different about this quantum state space, right? So the first key property that becomes important is the fact that if two vectors belong to the vector space, then any complex linear combination of these two vectors is also an element of the vector space. So these are the properties of a complex linear vector space, right? So if I denote by V, this kind of bold V as this is what denotes for me the vector space. Now the vector space is just like a set, right? It's a set, it's a collection of objects, right? Which we call vectors. So think of this as some collection of vectors. And for us, vectors are all denoted like this, right? As kets. Now, if I have two such ket vectors, V and W, and they both belong to, this is the belong to sign, right? And they both belong to the vector space, then any such linear combination also belongs to V, right? For all alpha and beta, which are complex, right? This is what I denote as this bold C often in my lectures, right? And herein lies the major difference between the classical and the quantum spaces. The classical space is just a binary valued object, right? Which can take one of two values, 0, 1, and that's it. Of course, you can construct higher alphabets, right? I can have an alphabet which has 3 elements and so on and so forth. But that is correspondingly scaled in the quantum case as a vector space of that dimension, right? So the classical space, which is simply a binary valued object, is now replaced by a 2-dimensional complex linear vector space. And what this means is I don't just have 2 possible states for the qubit, but any linear combination of these 2 states is also a valid state of the qubit, right? Anum, I just thought I'll mention the inner product idea as well briefly, right? So there are other properties that one associates with the vector space. For example, any complex number times V also is an element of the vector space. The sum of 2 vectors is also an element of the vector space. And in fact, this is what gives rise to this property, that any complex linear combination is an element. And finally, if it has to be considered a Hilbert space, then we need this idea of an inner product. And an inner product is something that takes 2 vectors and gives us a number or a scalar, as we call it. So this gives us a complex number. And the inner product in our case becomes important to understand concepts of orthogonal vectors and so on, right? Orthogonal states and so on. Okay. So specifically, finally, if one wants to talk about dimension, so for orthogonal states, let me just say that this inner product becomes 0. So the question of dimensionality between classical and quantum so what is a binary valued variable, right, in the classical case now becomes a 2D Hilbert space or a 2D complex linear vector space. And as we keep adding more and more bits, so if I now want to talk about a system of n classical bits, the quantum analog would be an n quantum bit system, right? But n quantum bits correspond to a 2 to the n dimensional complex linear vector space. And so this is what one often calls this exponential scaling of the dimensionality, that what is a system of n bits has now become a 2 to the n dimensional space. So Anu, maybe I'll stop here. If you think there's any aspect that are not answered, please feel free to ask me.
Yeah, thanks, Prabha. Actually, you covered two questions. So the next question was, what is n bits and how does it translate to 2 to the power n dimensions in the quantum space? So thanks for answering that. And because you have been mentioning complex numbers, so there has been a question around, why are complex numbers specifically introduced in quantum computing? So do you want to introduce phase and explain phase probably here?
Yeah, I can do that. Just one final point to note, since you said there's a specific question about n bits becoming 2 to the n dimensional complex linear vector space, the way to understand this would be the following, right? So if I had just a single bit 0, 1, that gets replaced by vectors, that gets replaced by anything which is the a complex linear combination of ket0 and ket1, right? So this is 2D space, right? 2D linear vector space. LVS is short for linear vector space for me. Now, if I have two classical bits, okay, then what are the possible states? I have 0, 0, 0, 1, 1, 0, 1, 1. And this in turn corresponds to a set of 4 states like this, 0, 0, 0, 1, 1, 0, 1, 1. And this is something that gets covered also in week 2. We go over this aspect of multi-qubit systems. So this will get covered in greater detail. But just note that what was 4 states here, right, now becomes 4 states that form a basis, right? So when I have 4 states that form a basis, that basically gives me a 4-dimensional complex linear vector space, or in other words, a 2 to the 2 dimension complex linear vector space, and so on and so forth. So now if I have n-bit strings, they will correspond to the quantum analog would be 2 to the n dimensional complex LVS and states in 2 to the n dimensional complex LVS. Okay, just to complete this point about how n becomes 2 to the n. Okay, so the third question was about why complex, right? Okay. So I can answer this question in 2 ways, okay? The first is what I would call the physics answer, which would say that suppose I write these superpositions, right? So consider a qubit system, okay? And remember the physical example that we gave for a qubit system was that of a spin-half particle, right? And for a spin-half particle, I can think of the spin along 3 different directions. And this is what we call the X, Y, and the Z direction. And if you recall, we worked out the operators, the states, etc., which correspond to all these directions. Now, physically, if I want to talk about what are the states that correspond to spin along Z, right? So if you recall the SZ operator, then this was associated with the eigenstates ket0, ket1, which formed our standard basis states. Then we went on to talk about the SX, right? And this had eigenstates which were linear combinations of 0 and 1 of this form. And note that there is no complex phase here, right? So this is what we call the plus minus states. And there is no complex phase. It's in fact just a, the coefficients are all real, right? But now if I want to talk about SY, okay, and this has to then give me another pair of orthogonal states, right? Then you find that if I stick to just real coefficients, then I have no more room, okay? Then I do not have room to have another pair of orthogonal states which are going to represent the Y eigenstates. And in order to do that, I have to start introducing a complex relative phase, right? So this becomes a complex relative phase, and this relative phase, the complex phase actually is what leads to non-trivial effects of interference, right, which then get reflected in the probability amplitudes, right? So this whole idea of quantum interference, whether one looks at it from a Young's double slit experiment point of view, or if you want to look at it from the point of view of having a way to represent all the physical states, the physically accessible states of the system, you cannot describe these states without introducing this complex relative phase, right? Now, from a computational point of view, it is this complex phase that gives us the computational power, that gives quantum computing its computational power. Because computationally, I could also, for example, talk about what is called a rebit. Okay, this is, so people thought about this, the pioneers of quantum computing did think about this. They thought about, can we just have a real qubit? And will a real qubit have the kind of computational power that the actual quantum bit, which we describe using complex phases, have? Well, the answer is, of course, no, right? So this will not have the computational advantage that a complex or the actual qubit will have. Okay, so the rebit will not have the power of a qubit. Okay, and another way to think about it is via the Bloch sphere, where if you're restricting yourself to the rebit, then you're really not accessing all the states on the surface of the Bloch sphere. So if you recall, any state on this, please excuse my drawing, this is my idea of a sphere, but note that any point on the surface of the sphere denotes a state of a qubit, right? So a single qubit can access all of the points on the surface of the sphere, whereas a classical bit can only access, let's say, these 2 points, right? So if this is my classical 0 and classical 1, and then remember that we also marked the quantum 0 and the quantum 1 on this. I think this is there in Dr. Rama's lectures, right? So note that this already gives you a glimpse of this exponential power that we've been talking about, right? Because instead of just accessing 2 points on the surface of the sphere, I'm now accessing the entire sphere. But if I were to restrict myself to a real qubit, then you can see that you're cutting yourself off from 1/2 of the sphere. You're only working with one hemisphere, basically, right? And so obviously that you're not accessing the full computational power of the qubit if you're restricting yourself to real bits, which have only real coefficients. Okay, maybe I stop here, Anu.
Yeah, thanks, Prabha. Thanks for clarifying that. And you've already covered qubit and real bits, and because you went on to Bloch sphere, so the next question maybe, so there is a category of questions around Bloch sphere. So people are asking, why are the states Ket0 and Ket1 not represented orthogonally in Bloch sphere? Or why is the basis state represented parallelly in the Bloch sphere representation?
Okay, so maybe I will take this question, and then the other Bloch sphere questions we can direct to Dr. Rama as well, because I think some of the visualization aspects are covered in his lectures. Yeah. So let me just address this question about representing orthogonal states on the Bloch sphere. This is a very nice question, actually. So I guess everyone has noticed that when I draw this Bloch sphere, so let me just use the sphere that I've already drawn. So I marked Ket0 right at the top here, and Ket1, so the north pole is Ket0 and the south pole is Ket1, right? And we know that Ket0 and Ket1 are orthogonal in the inner product sense, right? But if I want to think about the vectors that represent Ket0 and Ket1, and let me draw this with a different color, just to distinguish. So if I think of this as one vector R1, okay, which is the vector in real space, okay, which corresponds to this point at the North Pole. And I write down another vector here, which I call R2, okay, which is the vector which corresponds to the Ket1. Okay, maybe I can call these R0 and R1 actually, that's better notation. So now notice that this R0 dot R1 is actually not 0. And this is the question that is being asked. Why is it that orthogonal states orthogonal quantum states, right, somehow do not seem to correspond to orthogonal vectors, right? So when I say states, I mean, of course, quantum states. They do not correspond to orthogonal vectors. Rather, they seem to correspond to actually anti-parallel vectors in the real vector space, in the real 3D space, okay? So in fact, R0 is minus R1, right? That's what I mean by anti-parallel. R0 is minus R1. And so there is actually a formula that we can do, that we can write down to map the quantum inner product of any two states on the Bloch sphere. So let's say that psi and phi are arbitrary qubit states, okay? Then one can relate the modulus squared of this inner product with, so let's say that psi and phi, corresponding to psi and phi, I have the real vectors that I associate with them are some A and B, okay? They are the 3D real vectors. I mean, these are real vectors characterized by the corresponding theta phi's, right? There will be a cos theta, sine phi, cos theta, cos phi, and sine, cos theta, sine theta, cos phi, etc. associated with A, and similarly with B, right? So let's say A vector and B vector are the real 3D vectors associated with these on the Bloch sphere. Then one can actually relate these two. So actually this becomes equal to 1 plus A dot B by 2, okay? Deriving this formula is, I would say, beyond the scope of this course at this point. So we don't need to worry about the derivation of this formula. And this is also a bit outside the course curriculum, I would say, at this point. But because people want to know, I'm just mentioning this, that there is a nice connection you can make. And so now you notice that if you just take this formula as given from me and don't worry about how it came about, now you notice certain facts, okay? So if psi phi is 0, then that implies that A dot B is actually minus 1. And that is in fact what you notice all the time, that whether it's the plus and the minus state, or so this is the plus and the minus, or the plus I and the minus I states, right? They're all anti-parallel vectors. So orthogonal states, that's why they live on the opposite ends of a diameter. They are anti-parallel vectors in the real vector sense. And what is more, you can notice that the other way around, that if A dot B is 0, which means that in the real vector sense, they are orthogonal vectors, then you notice that this inner product, mod squared, is actually a half. And what kind of states do you know which have this property? Well, you think of the 0 and the plus, or, you know, the 0 and the minus, or the 1 and the plus, or the 1 and the minus, right? So these are actually the states which are not orthogonal, which actually have an overlap. They correspond to A dot B being 0, okay? So let me stop here, and maybe Rama can take some questions.
Yeah, thanks, Prabha. Thanks for the detailed answer on these questions. So, so yes, Rama, I would actually ask you to take there are a couple of questions around your section wherein people are asking what is the half angle in the Bloch sphere. So would you also like to share your screen and show and talk about the Bloch sphere, since you have a couple of representations in Bloch sphere?
Sure. Let me navigate to the slide. I think they are asking the question about. Give me a second. Okay. You can see the full screen?
Yes, I can see your full screen. Yeah.
All right. So this is the basic, this was the introductory representation of the Bloch sphere in the slides. You can see the x-axis, y-axis, and z-axis, and the basis states 0 and 1 are represented at the extremities of the z-axis, right? Okay. Now we go to how we can represent an arbitrary qubit. That is not one that is at either endpoints of the three cardinal axes. So we have a qubit Q, an arbitrary qubit, which, as you all know and has been explained earlier, is a complex linear combination of the basis vectors get 0 and get 1. Alpha and beta can be any arbitrary complex number. Okay, so how do you represent any arbitrary complex number? We'll use polar coordinates here, and they have there's a modulus represented by an r and an argument represented by a theta. So this representing it in polar forms makes it easier to do the computation. So that's why we do that here. And our Bloch sphere is supposed to be a, by the way, just stepping back a bit, why do we use a Bloch sphere? Why do we use any means of visual representation? It's because we want to be able to, plot any basic computational unit of our system on that using that tool. And second, we want to be able to show how any transformation of our basic computational units can happen. Okay, the Bloch sphere serves that dual purpose. So we have a qubit Q, which any qubit of any single qubit, that is the linear combination of the 0 and 1, can be mapped to a unique point on the shell of a Bloch sphere. That's the whole idea. That's why we use the Bloch sphere. So by that logic, you're going to have, if you see the coefficients alpha and beta, if you take the moduli, the sum of the squares must add to 1, because this is a unit sphere and the radius is always 1. Okay. Now note that this is independent of both the arguments theta 1 and theta 2, and so we can take taking a completely different value theta. It's not unrelated to theta 1 and theta 2. We can just assign R1 as the cos of a particular angle and the R2 as the sine of the same angle, right? So basically trigonometry tells us that the square of a cos and the square of sine add to 1, right? Why do we take theta by 2 rather than theta? That's because when we plot an arbitrary qubit on the Bloch sphere, we can plot it, it will always be in such a way that the value, the angle of that qubit vector to the vector 0 happens to be this angle theta. And in mathematical terms, if you have to represent a qubit, that actually is theta by 2. And this is, if you go back to the explanation that Dr. Prabha gave about relating Hilbert space to about representing qubit in Hilbert space, the Bloch sphere is a 3D representation of a qubit. Now, if we just think of if we can relate our qubit to our two-dimensional space as a linear combination of two vectors that's on a single plane, there our basic axes are perpendicular to each other, and there, because our qubit's mathematical representation uses that notation, which is roughly equivalent to how you would represent a vector, a 2D vector using the unit vectors I and j as ai plus bj. It turns out that the angle that you would have between the qubit q on a 2D plane or on a Hilbert space-like plane happens to be half the angle you would get in the Bloch sphere. Relating the Bloch sphere to your 2D plane, on the 2D plane, you would have the 0 and the 1 perpendicular to each other. Here, they are at 180 degrees with each other. Therefore, naturally, if you have a qubit that's represented on 2D plane at a particular angle, theta with the x-axis, here on the Bloch sphere, the angle with respect to the 0 vector, which is one of the basis vectors, is going to be double that. And that's really what we are showing here. So the fact that this angle theta by 2, that's half of the angle that you see between the vector q and the 0 vector on the Bloch sphere, is an artifact of how we of the fact that we use a Bloch sphere at all to visually represent a qubit, and it's a better way of representing it than 2D space because we can show any arbitrary rotation. And by the way, you learn about, if you've not learned about already, you learn about rotations of qubits as being linear transformations, and quantum gates are the vehicle by which you do that. You'll learn that later. A Bloch sphere allows us to represent any given qubit as a point on a shell, and any transformation of a qubit is moving that point from moving the qubit from one point in the shell to another point. And that's all we need really to represent a single qubit and a transformation of qubit. So the Bloch sphere is powerful, and is powerful enough to do any basic operation of single qubit. It's just that when we translate the qubit, the basic qubit expression to how it's represented on a Bloch sphere, the angle ends up being double because of the nature of the Bloch sphere. I hope that is understandable to people. Anu, you have
Yeah.
okay.
Yeah, that helps. So we had a lot of questions around it, and I would also urge. So I see this question also came on YouTube live on the chats, and I hope this is answered. And people who are asking related questions, you can go up, scroll up. I think there's a lot of questions around where is the Discord server link and so on. So you can just scroll up. These have been answered. Rama, I'll take one. I'll have one more question for you. So since you're sharing your screen, if you could just go back to the derivation of Hadamard gate matrix equivalent. People have been asking about the derivation and also about the phase shift between Z, X, and Y. So the polygate phase shift.
Let's start with this video. Let me, on this slide deck, let me open the other one. Hello? Anu, you can hear me, right?
Yeah, we can hear you perfectly. Yeah.
Let me open the other day. Okay, which slide do you want me to go to?
Yeah, so yeah, but this is also okay. Yeah, this is
one, and yeah, the next one has
the Hadamard.
right?
Yes,
yeah.
Yes, these two derivations.
All right. Okay, so this was what we started with as examples of single qubit gates, the poly X, Y, and Z gates. And the poly X gate is a gate that I think, as we introduced right in the beginning, is a gate roughly the equivalent of the NOT gate in classical computing. The NOT gate is the simplest gate that you can have in classical computing. It flips a bit, turns a 0 into 1 and 1 into a 0. In the quantum in quantum computing, the most intuitive way to think of it is what's a gate that can convert a ket 0 into a ket 1 and a ket 1 into a ket 0. Okay, but of course, as you know, we don't have just ket 0 and ket 1, right? Our qubit Q can be any arbitrary complex linear combinations of the two, which is you get into it's in the complex number space. So our conversion of any or rather the what we call the so the poly X gate is essentially doing a NOT, or it is doing a bit flip on any arbitrary qubit. What does that mean? It means that before we go to the sphere, let's just look at the matrix here. Okay, this is the matrix that it's used to represent this, and this is the Dirac equivalent. I hope this is understandable to people if you have seen the preceding slides. Let's go to the sphere. So the poly X gate, as I mentioned, it can flip 0 into a 1 and a 1 into a 0. Okay, and that's shown by these derivations. Now you can pick whichever mathematical framework you find more intuitive. Matrices, I think most of you probably already know, even if you have not done a course in linear algebra. Just a matrix multiplication. You know how to represent a single qubit as a column vector. You have matrix, which is a for a single qubit, the matrix transformation is a 2 by 2 matrix. So you do the multiplication, ket 0 turns into ket 1. Okay, and same way if you do the multiplication on ket 1, put 0 here and 1 here, you'll see that turns into 1. Okay, flip is easy. Again, in Dirac notation, I find this quite intuitive. If you do the take the Dirac expression and then you distribute the this expression into the or rather you distribute the get into the expression here, you'll end up with different kinds of bracket combinations, and once you get the basic hang of it, you can do computations pretty easily. So you see similarly a 0 will turn into 1 and a 1 will turn into 0. Okay, what is the more general understanding of this the poly Qiskit is that if you're applying it on not just a 0 or a 1, if you're applying it on an arbitrary quantum bit with coefficients alpha and beta, you end up flipping the beta and the alpha. What that means is that the probability of this qubit resolving, what do alpha and beta mean? They mean that they are the probability amplitudes, right? They give you a measure of the probability of the state collapsing to a 0 or collapsing to 1. In effect, you're flipping those probabilities. So you have so that in effect is what it does. It is going to be reflecting this bit from one hemisphere to another. That in effect is what's going to happen. And if you can try this, by the way, when you're coding. The visuals that you see here these are generated from the Jupyter notebook. So whenever you start doing your programming, you can generate these visuals quite easily, and then you'll be able to visualize how a particular gate converts your given qubit, whether they be single qubit or multiple qubits, which are also explained in this lecture. And you can see that pretty intuitively. And always use the API features to render your qubits out on Bloch sphere, and that you'll find that they're very intuitive to understand. Okay. So the poly gate or the poly Z gate is doing something a little different. It's also doing a rotation around on the Bloch sphere by pi. Or 180 degrees. It's just that it's instead of the rotating around the x-axis, the poly Z gate is going to rotate your qubit around the z-axis. So the z-axis is the vertical line. Okay, so you have any qubit, it gets rotated that way. For the poly X gate, like this is, think about the X gate x-axis oriented this way, and you're just going to be rotating it around that. Okay. Similarly, the poly Y gate it ends up flipping both the bit and the phase. If you do the math, if you experiment with it, you'll see that is the case. And visually on the Bloch sphere, you end up naturally, that's why we call it a Y gate. You end up rotating the qubit around the y-axis by rate. I'll skip over that part for now. Hadamard gate is a gate that rotating by pi is one thing, but we would like a more powerful gate, something that can rotate by a fraction. So that's really why we use the Hadamard gate, and it's useful because it allows us to rotate a qubit by 90 degrees. In this case, if you have a qubit representing the basis state 0, and suppose you want to get the basis state x, okay, and there is a very compelling reason to do this, and literally all quantum computations that you're going to encounter are going to use this transformation. Almost all circuits will begin with the Hadamard gate, where because physically what you do in any quantum computing system is you start with what are called the ground states or low energy states, and which are all going to be in get 0. Okay, you can have one qubit or you can have n qubits. You're going to be starting with 0. Then you want to be able to do some computation on the states. Okay, now how do you do this computation on the states? You can't just do computation on 0 states. That doesn't serve any purpose. What you want is the ability to be able to generate superpositions of state 0 and 1, and then because from n qubits gives you a 2 to the power n state space, as Dr. Prabha explained a little while ago. You want the ability to produce to convert your zero state into a state that has some non-zero probability of both collapsing to zero and then collapsing to one. And then you can do a lot of smart computation on those, so you get an answer to a problem that you're looking for. Okay, the most straightforward thing you can think of is therefore given by this Hadamard gate, and that's why we use this law. It turns to a zero and into the vector that you can see represented at the end of the x-axis. Okay, and what is that? That we have seen earlier. It is the an equal linear combination of the 0 and 1 vector, and it has coefficient 1 over root 2. So the probabilities add up to 1 over root 2 squared plus 1 over root 2 squared. That's 1. So it's a normalized vector. The Hadamard matrix is represented by this, and in Dirac terms, it's what you see here. And if you apply it to the vector 0, you can see, do the matrix multiplication, you get the vector at the end of x, which is nothing but our plus vector. Okay. Similarly, to apply the same thing, apply the Hadamard gate, that is, multiply this matrix with the vector plus, you end up getting back your zero state. Okay. So this is very useful in computation that you'll see later. Did I cover that enough, Anupama? You want me to cover other gates?
No, Rama. I think that's very good elaboration, and I hope that answers this question. And I request others to go back to this, probably the YouTube live, and also this is explained in module 1 of week 1. In module 2, in week 2, we are going to cover how can you generate these Bloch spheres on IBM, on Qiskit, or even on IBM Quantum Composer. So stay tuned for that. And once you start seeing these Bloch spheres in action, I think that's going to help understand in more detail. So thanks, Rama, for answering this question. And there are a couple of questions on chat. Shesha, do you want to cover a couple of technical questions on that I see on chat?
Actually, I want to ask, I just jotted down some of those questions. Maybe these questions are for Prabha. So I'll read out these questions, the related questions. Prabha, maybe you can pick them and answer. The question is related to postulates and unitary. So I'll read out the question. A couple of them are there. So in postulates of quantum mechanics, this is the second postulate from what he has written. The first point under unitary operators was that it can be derived from the time-independent Schrodinger equation, but the equation itself had the term t. So the question is asking is why time-independent? Second related question, also the result of unitary u t comma t0, that is evolution from t0 to t, has the exponent e power minus h, you know that, also contains t in it. So he's asking, the student seems to be confused about time-independent Schrodinger equation while there is a time in the term. So maybe you want to clarify that.
Yeah, sure. So actually, the equation that is written down in the lecture is not quite the time-independent Schrodinger equation. It is in fact the time-dependent Schrodinger equation, right? So maybe let me just share screen again and write this out quickly. So anyway, so this was another point that had come up. So I just jotted down this observables, eigenvalues, and eigenstates. If I have time, I can go over that. But this question on Schrodinger equation. So there are two ways of writing down. Of course, people know that there's a time-dependent way and there's a time-independent way, right? So when I say time-independent Schrodinger equation, that is essentially an equation of the form that I've written down here. Actually, it is what is called an eigenvalue equation. Okay. So the eigenvalue equation simply says that the Hamiltonian acting on some state psi will give me the corresponding energy. So if this is an energy eigenstate, so let me write this as EI, will give me some energy times EI, right? So this is what we call a time-independent equation because there is no explicit time written out here, right? So this is the time-independent Schrodinger equation, which is simply an eigenvalue equation, which says that EI, this ket EI, is an eigenstate of this operator H, which is what we call the Hamiltonian, which is the operator associated with the energy observable. This is the Hermitian operator that's associated with the energy observable. the time dependent equation, which is what governs time evolution, right? Oops. Right? This is of the form del psi by del t. So this is a IH bar maybe is H times psi, right? Now this is a differential equation in time. Now what I had said in the lecture is that there's an easy way to write down the solution of this if the H, which is the Hamiltonian itself, is time independent, okay? So maybe that was what was confusing in what I had said. So what I had mentioned was this Hamiltonian itself can sometimes be a complex function and it can be a function of time, right? But if H is not an explicit function of time, so this is not a function of time, okay, then I can write down a solution to this equation, which is of the form psi at time t goes as e to the minus I H t by H bar acting on psi of 0, right? So this is what I had said, that if this Hamiltonian H is not a function of time, for example, in the case of a spin half particle, the Hamiltonian is simply some number, this is which comes from physics, doesn't matter so much, but it could simply be some number times sigma z, right? It could simply be some number times sigma x. This itself could be a spin Hamiltonian. Sometimes you could have, if I have a pair of spins, then the Hamiltonian could simply be a product of sigma z, sigma z. Now, the Hamiltonian itself is not changing with time, right? Which means the energy relations of the system are not changing with time, right? The Hamiltonian simply describes the potential and the kinetic energy of the system, if you will, right? So this relation is not changing with time. Then I can write down a solution for the Schrodinger equation of this form, which then gives me a unitary operator. So this leads to the time evolution operator from time t0 to time t. So then I write down psi at time t is this unitary acting on psi at time 0. And all quantum evolution, in fact, happens via unitaries. Let me just make a point here that even if the Hamiltonian is dependent on time, we can still write down this unitary. The evolution is still unitary. It's just that this unitary is not so easily related or so easily derivable from the Schrodinger equation. You can't simply read it off. You have to do a bit more algebra to get to this unitary operator that governs the time evolution. That's all. Okay, I hope that clarifies the issue.
Yep, thanks, Prabha. There are a couple of related questions on the implementation or realization. So I'm going to read that out. You can give a brief perspective on it. So how qubits are storing in quantum computer, how to access the qubits. I presume the question is related to the physical realization. The second one on similar lines is, I don't fully get what a state really means. Do each electron have its own state? Do photons have them as well? Do atoms have multiple states corresponding to each of electrons? So there seems to be questions related to realization and what is a state in the quantum sense.
Yeah, so qubits can be realized in several ways. And I think I had described probably 3 examples of this in the lectures that I had given. So when I say a physical realization of a qubit, any 2-level quantum system is a qubit, right? Any quantum system where I have primarily 2 levels, 2 energy levels that the system accesses. These could be spin half, plus half, minus half. These could be 2 different polarizations. These could be the ground state and the excited state of a particular atom, etc. So when I have access to exactly 2 states of the system, 2 distinct energy states, right? Then that's what I refer to as a qubit. How do I store information? Well, I have to then have a collection of spins, let's say, right? So this, for example, is what is done if I have what's called an NV center qubit, right? There are nuclear spins. You have an array of them. And this collection of nuclear spins is all set to whatever state you wish to store. If you wish to store a 0 in the first instance, it's just the ground state, let's say. If you wish to store a 1, then you have to do some rotation like the Bloch sphere rotation that Rama was talking about and get to the 1 state and then store it. right? And if you want a plus state, if you want a minus state, etc., whatever superposition you wish to store, you prepare your spin, right? Let's say you start with the 0, which is the north pole, and then you rotate on the Bloch sphere to whatever desired state. Now, storing a qubit is hard, and this is what we will see in week 4, where we'll see that qubits are highly susceptible to noise. So if you prepare your qubit in whatever state you wish to, it is not going to remain in that state for very long. It is going to undergo something called decoherence, and this is actually discussed in a couple of lectures in week 4, right? The other question was relating to what do you really mean by a state, right? A state is a description of the two-level system, right? Is the two-level system in the ground state? Is it in the lowest possible energy state? Is it in the first excited energy state? Is it in some combination of these energy states, right? So the state is a mathematical description of the, if you wish, the energy of the system in some sense, right? If you're talking about photon polarization, then it tells you something about what is the axis along which the electromagnetic field is oscillating, the electric and magnetic fields are oscillating for this particular photon, right? If I say that a photon is in a particular polarization state, then it means that for this photon, the electric and magnetic fields are oscillating along a particular direction. That's what it maps back to, right? Now, what quantum mechanics tells us is it is not possible for you to intrinsically assign such a state until you really measure. So there are two aspects to this. You prepare. When you prepare, you know what state you're preparing exactly, obviously. But if you, as a receiver, if I receive an unknown quantum state, or in a computation, if I do various gate operations, and then at the end, I want to know what is the state, then I must measure, right? And it's only when I measure that I collapse my system down to a definite state. And this becomes a probabilistic process, right? So when I measure, I know exactly what state the system has collapsed to. I can read off some value and associate a certain physical value, for example, to polarization or to spin or to energy, whatever the observable that corresponds to that particular status, right? So I hope that answered the questions that you had asked.
Yeah, thanks, Prabha. I think we are almost out of time. Anu, is there any last minute things that we need to cover?
No, so the other questions, maybe we'll just answer over Discord. And yeah, I request all of you to be on Discord, where all the mentors are answering these questions. So thank you, Prabha, and thank you, Rama, for your time.
Thank you all.
Thank you.